You settle into seat 23A, pull down the shade, and there it is, a tiny rounded window in a giant metal tube. Not square, not even a neat rectangle. Every passenger window on almost every airliner has had its corners carefully erased, as if the aircraft industry declared war on 90-degree angles. That shape is not decoration, and it is not there because clouds look better through an oval frame. It is the visible scar of an engineering lesson learned in the 1950s, when the world's first commercial jet airliner began breaking apart in the sky. And here is the uncomfortable part. The danger was almost invisible until it was too late. Most people hear the simple explanation: square windows are weak, round windows are strong. That is close enough for a trivia card, but it hides the interesting bit. The glass was not simply cracking like a window hit by a football. The real problem lived in the aluminum skin around the openings, where pressure, shape, manufacturing marks, and repeated flights combined. Picture a paper bag filled with air. Push outward from inside, and every part of the bag carries tension. Now cut a hole in it. The force has to flow around that hole. Smooth curves guide the force around gradually. Sharp corners make it crowd together, creating a stress concentration, a tiny area working much harder than the rest. You would think the glass was the weak part. Nope. The dangerous part was often the metal surrounding the hole. A squarish opening can make stress pile up near its corners. One flight may do nothing obvious. 10 flights may do nothing. But metal remembers repeated strain in the form of fatigue, and fatigue is patient. Modern passenger windows are therefore not perfectly circular. A circle would handle pressure beautifully, but it would waste space and give you a smaller view. Designers use ovals or rounded rectangles. Enough straightish area to see the wing, enough curve to keep stress from gathering in one angry little corner. Engineering is often a compromise wearing a safety certificate. The story begins in post-war Britain. Aircraft maker de Havilland wanted to leap beyond propeller airliners and build something almost futuristic, a passenger aircraft powered by jet engines. The result was the de Havilland Comet, with 4 engines buried inside its wing roots, a smooth silver body, and a cabin quieter than the piston aircraft passengers knew. On May 2, 1952, the Comet entered scheduled service with Boise, flying from London toward Johannesburg. It was the world's first commercial jet airliner. It carried about 36 passengers, cruised around 450 miles per hour, and flew high above much of the weather. To people watching it arrive, the future had shown up early, and it had excellent cheekbones. Flying higher created a new challenge. Outside the aircraft, the air was thin. Inside, passengers needed enough pressure to breathe comfortably. So the Comet's cabin acted like a pressure vessel. During every climb, the pressure difference pushed outward on the fuselage. During descent, that difference faded. The metal expanded slightly, relaxed, then repeated the routine on the next flight. Your question: how many times can you bend a paper clip before it breaks? Now imagine the paper clip is an airliner. The bending is tiny, but the cycle matters. Engineers understood metal fatigue, yet commercial jets were entering a new world of higher altitude, greater pressure differences, thin lightweight structures, and thousands of repeated pressurization cycles. The Comet had windows and other openings with relatively square shapes and rounded but tight corners. Its structure also used riveted joints and thin aluminum skin to save weight. None of those choices alone meant disaster. Together, however, small imperfections around holes could start cracks, and concentrated stress could help those cracks grow each time the cabin was pressurized. The first warning came on May 2, 1953, exactly 1 year after the Comet entered service. BOAC Flight 783 broke apart after taking off from Calcutta during a severe thunderstorm, killing all 43 people aboard. Investigators blamed structural failure caused by violent weather loads or possible overcontrol. That conclusion made sense at the time. The deeper pattern had not revealed itself. Then came January 10, 1954. BOAC Flight 781 left Rome for London. Around 20 minutes later, while climbing near 27,000 feet, a radio message stopped in mid-sentence. Witnesses near the island of Elba saw wreckage falling into the Mediterranean. All 35 people aboard were killed. There was no thunderstorm to provide an easy explanation. How do you investigate an aircraft that has scattered itself across the bottom of the sea? Piece by piece, British teams recovered wreckage from the Mediterranean and brought it to the Royal Aircraft Establishment at Farnborough. Engineers arranged the fragments on a wooden framework, rebuilding much of the fuselage like the world's worst three-dimensional jigsaw puzzle. The Comet fleet was grounded while investigators searched for causes: engine failure, control problems, fire, turbulence, explosive decompression, structural weakness. De Havilland made several modifications, but fuselage fatigue was not yet treated as the main suspect. Officials believe the possible causes had been addressed, and the aircraft returned to passenger service on March 23, 1954. Just 16 days later, on April 8, South African Airways Flight 201, operated with a BOAC Comet, left Rome for Cairo. It broke apart over the Mediterranean near Naples, killing all 21 people aboard. Two similar disasters in calm high-altitude flight could no longer be explained away. The Comet's certificate of airworthiness was withdrawn, and the fleet was grounded indefinitely. The investigation now became one of the largest engineering detective stories of its time. Sir Arnold Hall and the Farnborough team needed to reproduce years of flying without risking another crew. BOAC supplied a Comet fuselage, registration GLYU, and engineers placed nearly the entire aircraft inside an enormous water tank. Water was the clever part. Filling and pressurizing the cabin with air could turn a failure into an explosion. Water is far less compressible, so when the metal tore, the energy escaped more gently. Hydraulic rams also loaded the wings while pressure rose and fell, allowing investigators to imitate the stresses of repeated flights again and again. The test aircraft had already completed 1,230 pressurized flights. In the tank, engineers added another 1,830 simulated flights. Then the fuselage failed at a corner of a forward escape hatch opening. Big number, big clue. The structure failed after about 3,060 pressure cycles, far earlier than expected. The invisible enemy finally left a visible tear. Investigators examined the metal under microscopes. They found fatigue cracks beginning around openings, rivet holes, and areas where stress was concentrated. Every pressurization cycle could advance a microscopic crack by a tiny amount. For a long time, the aircraft looked perfectly normal. Then the remaining metal could no longer carry the load, and failure raced through the fuselage. Now for the myth bust. The fatal crack identified in Flight 781 did not simply begin at the corner of the passenger window beside someone's seat. Evidence pointed to a rivet hole near the corner of an automatic direction finder, or ADF, aerial cutout, in the roof. It was an opening in the pressure cabin, fitted with a non-metallic panel for navigation equipment. So, did square windows kill people? The honest answer is, squarish openings were part of the problem, but the popular sentence is too neat. The disasters involved stress concentration around cutouts, thin skin, rivet and manufacturing details, repeated pressurization, crack growth, and test methods that gave engineers more confidence than the production aircraft deserved. One test had appeared especially reassuring. A prototype fuselage survived 16,000 pressure cycles, more than the Comet's intended service life. But it had first been pressurized to unusually high levels during proof testing. That process unintentionally strengthened, or cold-worked, some stressed areas. The test specimen behaved better than ordinary production aircraft. 16,000 successful cycles should have been wonderful news. Instead, they helped hide the danger. This is one of the most surprising parts of the story. De Havilland did extensive testing and exceeded the rules of the day. The company was not simply careless. It was operating at the edge of what engineers and regulators understood about repeated pressurization in large jet airliners. The solution was not merely to take a file and sand down four corners. Later Comets received redesigned openings, thicker skin, stronger structural framing, improved manufacturing details, and far more demanding fatigue testing. The Comet 4 eventually returned the name to commercial service, but by then American rivals had caught up, and Britain's enormous early lead in passenger jets had largely disappeared. The lesson spread far beyond one aircraft. Designers began treating every hole in a pressurized fuselage, passenger windows, doors, hatches, antennas, and cargo openings, as a place requiring special care. Curves became common, reinforcement became more deliberate, and full-scale structures were cycled repeatedly to expose fatigue before passengers ever climbed aboard. Here is the strange truth. Your airplane breathes on every flight. As it climbs, pressure loads make the fuselage expand slightly. As it descends, the loads ease. Airlines count cycles as well as flight hours because a short flight creates another full pressure cycle, even if it spends less time in the air than a long-haul journey. The Comet investigation also changed how engineers think about evidence. Passing one strength test does not prove a structure will survive years of repetition. A part can be strong enough today and still be vulnerable to a crack that grows slowly. Modern aviation combines design margins, fatigue tests, inspections, crack growth analysis, and planned maintenance rather than trusting one heroic test. And rounded windows became a visual shorthand for that philosophy. You see the same thinking in rounded door corners, smooth cutouts, and reinforced frames. Round does not mean perfect circle, and square does not mean instant explosion. It means engineers try to remove abrupt geometry wherever stress would otherwise gather, and then test the whole structure as a system. So the next time you sit beside that little oval, remember the one-line answer. Airplane windows are rounded because curves spread pressurization stress more safely than sharp corners. But the fuller answer is better. They are rounded because a beautiful new jet taught the world that metal can fail slowly, silently, and repeatedly, and because safety often arrives disguised as an ordinary shape you stop noticing. That small curve carries the memory of lost aircraft, painstaking tests, and an industry forced to rethink what strong really means. Now look closer at the window itself. Between the thick layers, near the bottom, there is usually a tiny hole. It looks suspiciously like a defect. It is not, and its job is another surprisingly clever story.